Now let's discuss about the partitioning methods for doing the clustering. So the partitioning methods are based on one very simple concept, which is that let's say there are a set of n objects and they be divided into k clusters such that sum of the square distances is minimized from the the centroids which are representing the clusters. So this is to say, if there are k clusters and for each point which belongs to cluster Ci, the the distance of p to the cluster centroid should be minimum. So how do we minimize? We use the square of the sum of the squares, and we sum it up for all the clusters, and then we have an objective function. And this is representing an error function or an objective function. And then this is so this can be a very high level conceptual definition for a partitioning algorithm which creates k clusters given a data of n objects. And this error function is becoming a globally optimal if they can exhaustively enumerate all partitions. But then we find that this is not a tractable approach even for large data, even for a very powerful machine. So we take a heuristic methods which are referred as some of the algorithms that we are going to see, k-means and k-medoids. These algorithms where k-means, where each cluster is represented by a center of the cluster, which is, for example, if there are 3 objects which belong to a cluster, then we have a artificial so we are representing in blue color a object which is non-existent, but then representing the centroid of the cluster, which is a notional object which is representing the centroid of the cluster. So that is what is becoming the k-means. So we are imagining a mean exists for each cluster, and thereby we are proceeding, and it has become very successful and popular, the k-means algorithm for doing the clustering. And there are alternate approaches. Some people think that the creating a notional or imaginary objects to solve the problem may not help in many contexts. So what they say is that they want to find a representative object for each cluster that they refer as a medoid. And then there are algorithms called k-medoids or partitioning around medoids, which are not that popular for simple reason that requires a lot more computation than imagining an object which is a mean. Okay, there is a question from Mr. Nagabhushnam was saying, do we need pre-processing for clustering as well? Yes, of course. The pre-processing is required because as we have discussed, there may be outliers, there can be noise, there can be a scaling problem. Normalization and scaling is itself is a pre-processing. So considering that we want to use multiple objects, each belong to different types, different scales. So we will certainly require pre-processing for clustering like the way we required for the other analytic tasks. So now let's look at a k-means clustering algorithm. So what we do is that this is a partitional clustering approach, and each cluster has a centroid, and each point is assigned to a cluster with the closest centroid, and number of clusters must be predefined, and then the algorithm, the pseudocode for the algorithm is simple. So select any k points as initial centroids. We may use some heuristics on how to select, but that's different. So in general, k means is start with k initial centroids, and then we form the clusters by assigning remaining points to one of these centroids, that which is we take it as a closest centroid. And after that, after assigning all the points to the k clusters, we recompute the centroid of each cluster. And after we recompute the centroid of each cluster, then what we do is that we are getting new k centroids. So we are going to repeat assigning the remaining points to the k clusters. And we keep doing that until we recognize that the centroids are not changing. So that is the simplest the representation or the pseudocode for a k-means clustering algorithm. So we can do it. Possibly we can take an example and see how it works. So now let me say I have 5 objects. So let me start with a two-dimensional object. So now let me see O1 each. O1 each, let me see 1, 2. Then O2, I can make it 5 and 7. I'm arbitrarily taking, so as we do O3, we are saying each, let us say 6 and 10. O4 each. Okay. So what will we do? We have to, let's say our intention is to create 2 clusters. Okay. So the k-means cluster expects you to give the number of clusters upfront. So 2 clusters. Okay. Uh, Mr. Vivek is saying, okay, there was some lag in seeing the whiteboard. Okay, I hope it has become visible by now that you are able to see 5 objects, and our intention is to create 2 clusters. Okay, our intention is to create 2 clusters. So okay, so now we need the initial centroids. So what we will do is that to start with, we will take the initial centroids as, let me take them as 1 each. Arbitrarily I'm taking, 1 is O2 and other is O4. Okay. So now, so what we will say is that let us say O2 represents so I will have O1, which represents cluster 1 to start with, and is it O1? I started with, okay, I can as well start with that also, but I thought I said O2, which is representing cluster 1, and then I have O4, which is representing cluster 2. So now what I will do is that For each object, I will see O1. I have cluster 1 and cluster 2. I calculate the distance from each cluster. O1, O2 is now only object in cluster 1. So it is 5, 7 and O1 is 1, 2. So what is the distance? It is 5 minus 1 and 7 minus 2, say 4 square plus 5 square. So that comes to the root of 41, right? Now let's see the distance of O1 to C2, which is O4. So this is 1 and then 2, so this is root of 5. Now I will so I have to do that same thing with the other objects. So O2, O2, now the distance from C1 is 0, right? And what is the distance from C2? O2 is 5, 7 and C2 is this. So this is the 3 and 3. So this is going to be root 18. Okay. So now I go to O3. So O3 is 610. I calculate distance from C1, which is this is 1 and 3. So this is becoming a root 10, right? And now what about the distance of O3 to C2? So this is 4 and 6. So this is becoming a root 52. Now let's go for object O4. Distance from C1 is O2 is this is 3 and 3. So this is going to be root 18. This is 0. Now let us find that for O5. O5 is 7, 9. Its distance from C1 will be 2, 2. So this is root 8. And then O5's distance from C2 will be that 5 and 5. So this is root 50. So now we can finding that O1 should belong to cluster 2, right? O1 should belong to cluster 2. And O2 should belong to cluster 1. O3 should belong to cluster 1. O4 should belong to cluster 2. O5 should belong to cluster 1. So now cluster 1 has got O2, O3 and O5. So now cluster 1 has got O2, then O3, then O5, right? And then what about cluster 2? This has got O1 and O3. So now what we have to do is that we need to represent a mean for the cluster 1. So this has to be represented by a new mean. What will this be? This will be O2, O3, O5. So 5 plus 6 plus 7, that is 18 by 3, so which is representing the cluster mean. Then 7, 10 and 9, 17, 26, it is 8.7. So, so this will be the cluster mean for cluster 1, and for cluster 2 it is 1, 2 and 2, 4. So this is going to be represented by 1.5 comma then 3. Just let me see. O4 is belonging to cluster 2, is it not? O4 belongs to cluster 2, and okay, O3 calculation is wrong. I did the mistake in calculation. Yeah, okay. So that is true. O2, C1 belongs to O2, O3, O5, and C2 is O1 and O4. Right? Thank you for pointing it out, Mr. Vivek. Which can be represented by a mean point O1 and O4, which is 1.5 comma 3. So now our next job is that this is the clustering that we have got. So we need to replace this C1 and this C2 by uh, C1 is becoming 6.6 comma 8.7, and C2 is becoming 1.5 comma 3. So we need to recalculate the distances. So we will erase these distances. So now we have to recalculate O1's distance to C1. So O1 distance to C1 is again 5 and then a root. So we are calculating the Euclidean distance. Euclidean distance is 5 square, and then this is 6.7 square. So 6.7 square will be about, I think it is point. So it's about 45. Then so this will be approximately, I'm putting approximate value. So this will be 5 square and then 6.7 square is to be 69. And then distance of O1 to C2 is 0.5 and then 1. So 1.25. Now let's look at O2. O2 distance is 1 and 1.7. So this is approximately root 3. Then what about this? The distance of 5.7 with this 3.5 and 4. So approximately root 28. Then O3, 6. This is 1. So this is approximately root 1 point. Oh, this is not approximately. We can get this accurately. So this is this O3 is 6, right? 10, and so this is 1.3. And O3 distance from here, this is 4.5, and so this is root approximately this will be root 70. Then O4, this is 4, and so this will be approximately 40, root 40. Then this one 0.5 and 1. This is 7, 9, so this is 1, and this is approximately 1.1. This is 5.5 and 6. This is again approximately root 66. So I'm not using calculator, so I'm putting approximate number. So now we can see that this should belong to cluster 2. Okay, this should belong to cluster 1. This should belong to cluster 2, cluster 1. This should belong to cluster 2, and this should belong to cluster 1. So now we can see that the C1 and C2 are unchanged. So what it means that there is no point in doing further iterations. We are going to get the same answers. So the k-means will come to a closure with this as the solution. Okay, centroids don't change, so that means the k-means can terminate. So now let's look at some more details related to k-means cluster. First thing is that the k-means initial centroids are chosen randomly. So if we have multiple runs, we want to do the still same k clusters, but if we don't get the first time we got some centroids and we use different centroids next run, we may end up with a different answer. And the centroid is considered as the mean of the points of the cluster, and generally the closeness is measured by Euclidean distance, cosine similarity, or sometimes by Manhattan. So there are several ways to measure, and many times k-means converges and converges within few iterations. So when you have a very large number of points, and then you may change the stopping conditions that until very few points change cluster. So you are doing it with 1 million points, and you are dividing them into 10 clusters. You see that only 5 points are moved from one cluster to another cluster. Instead of going for the next iteration, you may stop, saying that it's a very small change and I don't want to go further. And the amount of time that this algorithm will take depends on the number of points, because for each point we need to evaluate which cluster it belongs to, and number of clusters Because if there are k clusters, we have to compute its distance from the k centroids. Number of iterations, because for each iteration we need to repeat all the operations. And the number of attributes, because the number of attributes will decide the calculation of distance, whether the Euclidean distance, Manhattan distance, cosine similarity. Because for each one of them, the number of attributes decides the computational complexity. So all of them are multiplied. So the order of complexity can be taken as the product of number of objects, number of clusters, the number of iterations, and the number of attributes. And in the computer science, generally a algorithm which works linearly with these attributes is considered as a good algorithm, and that explains the popularity of k-means. Because for large data, if you apply k-means, you may be able to get the answers within hours. But if you apply a very complex another algorithm which has a different level of complexity, so n square and k cube kind of complexity, then it may take days and months. So let's see pictorially how does it represent. Suppose these are the original points. You can clearly see that there are three clear clusters. So an optimal clustering is, this is what we get. This is good. But then it's possible that the algorithm may converge to this point, and you can see here that the scope for changing the centroids is not there. Because if you look at this, I'm drawing the centroids with red color. Okay, so one centroid is here. Okay, another centroid is here, and third centroid is here. Now, in this inoptimal case, we can see that when we calculate the distance from centroid, none of the points are going to move away from one centroid to another centroid. So what it means that the algorithm has reached its termination condition. But you can see that we are ending up with suboptimal cluster. Okay, Mr. Vivek has a good question. We say we will randomly select centroids. So is it possible that we change the centroids and rerun the k-means algorithm? Yes, we sometimes do that and we can get better results. Right, we do that. Now let's evaluate the k-means clusters. So we want to know at the end what is the quality of the clusters that we got. So we can easily say that the distance of the object, any object from its centroid, can be treated as an error function. Because ideally we would like all the objects to be at one point, then we will have a no possibility of any doubt whether the object belongs to this cluster or not. So we can treat the distance as an error function, and we say that we want to minimize the error. So what will happen is that we will take the sum of the square as the objective function. Then the formula will come to this. So for each object, if it belongs to a specific cluster, we take the distance of the object from that cluster centroid, where M is representing the centroid of cluster Ci. So we take the square of that because we want to minimize the sum of the squares, and we do that for all the clusters. So that is, for each cluster you calculate the sum, and then you say that SSE is representing the sum of the squares for all the clusters for this algorithm execution and this clustering solution. So this can be treated as an objective function. What is Mr. Nagabhushan you're looking for? Yes, we can plot that, but then plotting that, yeah, we will see that when we plot the, we can plot the sum of squares versus the number of clusters, or for various solutions we can plot that. Yes, we can do that, but then we need to have a well-defined x-axis, right? So then only it makes sense. But then we can always take the advantage of the visualization to find the quality of the cluster. So suppose that we have got the same data, and two uh, initial centroids have been chosen, and as we know, based on the initial centroids, we may get a different solution. So we can look at this approach. Based on the initial centroids, if we choose, we will get this as the clustering, and if we choose initial centroids here, we are going to get the different clustering solution. So now what it means is that we have got two solutions, and if we have this is a small graph at two-dimensional objects, so we could easily see. But suppose we have got a million data objects, each is 10-dimensional, so visualization will be a challenge. Then only way we can compare each, we calculate sum of squared error for both the solutions, and we can compare, and we can choose the one with the smaller error. And one way to reduce, one in fact very easy way to reduce the SSE is to increase the number of clusters. Suppose there are n objects and we increase the k to n, saying that we want to create n clusters. So what will happen? We get sum of squared error is 0. But do we like it? We won't like it, right? I hope nobody has a doubt about that. If we increase the k, we can easily get good clusters, but that is not a solution in many situations. It is not a acceptable solution in many situations. We should get a good solution with small number of k. So importance of choosing initial centroids. So you can look at this. Suppose you start with three initial centroids like this. We have reached, somehow we have reached uh, converge to a good solution. So now let's choose the, so at the sixth iteration we got the good centroid. Now let us choose another set of centroids. So we got a final solution where there are two clusters here and one cluster here. Two clusters here and one cluster here. So this, at least we can see visually that this is not a good cluster. So now let's look at one real big challenge with the k-means cluster. Suppose that somehow we know that the data has got, so let me start one whiteboard. Suppose that we have got some objects. Now, how many natural clusters are there in this data? Are you able to see this? Okay, Mr. Vivek, you got the right. There are three natural clusters in this. Yes, yes, Mr. Nagabhushnam, you are right. There are three clusters in this. So now let us say our intention is that there are 12 objects, okay, and we want to make three clusters. Somehow we got it right. We somehow knew that there are three natural clusters. But then in this case, there are these are two-dimensional objects. We could easily visualize and check that there are three natural clusters. But then if each object is a 10-dimensional point, then we don't know how to visualize it, right? So we will not be able to tell, though there are natural clusters, we will not be able to catch them. We can try many projections and all that, but it's not, there is no easy solution. So now the challenge is, if there are so the k real clusters in that object, and the point is that we have to still pick up three centroids to start the k algorithm, is it not? K-means algorithm, we want to create three clusters, so we need to start with three centroids. So to get k clusters, we need to start with the k. So now, what is the chance of getting all the initial centroids from the distinct clusters, not from the same cluster, from the distinct clusters? So each centroid should come from each distinct cluster. So now let us say, for simplicity, there are n objects, okay, and then they are divided equally among the k clusters. So let's take a simple situation, because in our whiteboard we have got 12 objects divided into 3 clusters. So we generalize the problem, n objects divided into k clusters. So now, what is the probability that first centroid will belong to one of the natural clusters? It is 1, is it not? It has to belong to one of the natural clusters. So now let us look at the second object. Second object should belong to one of the remaining natural clusters. So what is the probability? What is the probability? It is can somebody tell me that? The probability is, so k minus divided by k. Has everybody understood this? How did I get this? I won't explain if you don't ask. Is this understood? So what is the probability that the remaining, okay, Mr. Nagabhushanam has asked, is it how? Okay, fine. Let me explain. Suppose the first object is from the one of the clusters, there is no doubt. So now what happens is that the second object I am again picking up randomly, so now I have to consider the probability. So each object has n by k points, okay? So now I have already chosen one cluster, so it should not come from that cluster. So what will happen, I have to go to k minus 1 multiplied by the number of points in the k minus 1 clusters are and then what are the total number of points? What is the total number of points? It is n. Okay, so now this is k minus 1 by k. Has everybody got it? Right? You got it? So it is k minus 1 by k. So now that is for the second object, second centroid. Now I have to choose the third centroid. Third centroid cannot come from either of these clusters. In that case, we are getting an overlapping. So third centroid choice probability will be k minus 2 divided by k. Is that fine? Okay. So now we go on until finally we end up with 1 by k. So this is the probability that we are going to get each object, each centroid from a distinct natural cluster. When we have a uniform clustering, that is natural clusters that are there in the data. So now you can see this formula. This will come to k factorial divided by k by k. When we choose k is equal to 10, the probability is less than 0.1%. So sometimes you choose any arbitrarily initial centroid, they will adjust themselves in a right way. Sometimes they don't. Fine, we stop here. We are overrunning the time. So any question till now you can ask me. Next class, as per the calendar, I think next week only we have the next class, right? I think tomorrow we don't have a class as far as I remember. Right? Next week. Okay, so if there are no other questions, we will stop.